In this video, I'm going to go over section 6.2, which is about one-to-one functions and inverse functions. So this should really be more of a review, but I'm going to go over a couple of these questions will be on your exam. So I just wanted to make sure I cover them, but hopefully you have seen this stuff from college algebra. So first, if you remember the definition of a one-to-one function, this is a function for if any two different inputs, then the domain corresponds to two different outputs in the range. So that is if x1 and x2 are two different inputs, two different x values of the function, then f is one-to-one if and only if the outputs do not equal each other. So we learned that in order for a graph to be a function, that the x values don't repeat. Well, for a function to be one-to-one, the x values and the y values both cannot repeat. So here are a couple of examples. The first one, this is a one-to-one function because we see each x value is only going to one y value. The next one is not one-to-one. It is a function because the x values are not repeating, but for the first two here, x1 and x2, they have the same y value. And then the last one is not a function at all because x1 has two images, y1 and y2. So the x value repeats there. So this example wants us to determine whether this set is a one-to-one function. So if we look at all the x values here, none of the x values are repeating. And the y value, so that means it's a function. And then the y values, none of those are repeating either. So it is one-to-one. Okay, so when we're given a picture of a graph, we can determine whether a function is one-to-one using the horizontal line test, which says that if every horizontal line intersects the graph of a function at most one point, then it's one-to-one. So here in this example of this graph, we see that this horizontal line is intersecting that graph twice. So therefore, this is not a function because those 2 points would have the same y value. So for another example, this function here is x to the 6th power, and you see that it is close to a parabola, and we have this horizontal line here crossing it more than one time. So that's not one-to-one. But the other one, we see that each horizontal line is only crossing the graph at one point. Here, 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 and here. So this is one-to-one. So for this theorem, it says that a function that is increasing on an interval I is one-to-one function on I. Any function that is continuously increasing. And similarly, any function that is continuously decreasing on an interval I is a one-to-one function on I. Okay, so now we're going to talk about how to find the inverse of a function, defined by mapping or a set of ordered pairs. So suppose that y equals f of x is one-to-one. The correspondence from the range of f to the domain of f is called the inverse function of f. So if we take the range from f of x and send it to the domain of f, then this creates the inverse function. And this symbol here is the symbol we use to denote the inverse function. it looks like f raised to the -1 power, but it just means that it is the inverse function of the original f of x. So if y equals f of x is 1-to-1 function, then f will have an inverse function f of this symbol here, and therefore x will be equal to the inverse function of y. We're replacing all the output values into that function, and they will now equal the input values. So in other words, what that says is that if we have a function f of x and the domain is equal to some interval, but I'm just going to say the domain is equal to c. Now this could be an interval or a number, and the range is equal to, let's make another letter d. Then for the inverse function, the domain will now be the range, which would be d, the range of f of x, and the range will be the domain. So this will now be c. Everything gets switched. So we have a set of relation here at these points, and then we're asked to find the inverse of the following. All we would have to do is switch all the x and the y values. So for the first point, we have -3 and -15. So down here is the set of points of the inverse function of this function, and you can see that they're switching the x's and the y's, so it'll become -15, -3. The next one from the original is -2, -10, so now we would have -10, -2, and so forth. So you're just switching all the x's and the y's to find the inverse. And so we see that the domain of the first function, the original function, is all of these x values, and they will become those will become the range in the inverse. And same thing for all of the values in the range of the original will become the values in the domain of the inverse. Okay, so the graph of a 1-to-1 function and the graph of its inverse are always symmetric with respect to the line y equals x. And here is that line right there through the origin. So this is an example of a graph f of x in blue and its inverse in red. So you can see that it's symmetric about that line y equals x. So for example, they want me to find the graph of the inverse of this function graphed here in the Cartesian plane. So they just have this two line segments being connected by the points -2, -1, or yeah, -2, -1, and 1, 0, and then to the point 2, 2. So to find the points of the graph of the inverse, all we do is switch the coordinates. So if I have 2, 2 here, if I switch those coordinates, I would still have 2, 2. So here's the point on my inverse function. And then the next point, 1, 0, this would become 0, 1, so that would be right here. And then the last one is -2, -1, so that will become -1, -2, which would be right here. And if we connect those points with lines, it makes this graph, and that is symmetric with the line y equals x that goes through the origin. Okay, so like I was saying, the domain of the original function f is equal to the range of the inverse of f. And the range of the original function f is equal to the domain of the inverse. So they just get switched. So we can actually determine whether two functions are inverses of each other by plugging them into each other. And if they result in x, then we can conclude that those two functions are inverses of each other. And you can show this either way. You can plug in the original f of x into the inverse, or you can plug in the inverse of x into the original, and both ways should equal x, and that will show you that they are inverses of each other. So for example, it says verify that the inverse of g of x is equal to x to the fifth is the inverse of g of x, which is equal to the fifth root of x. So to verify that these two functions are inverses of each other, I am going to find the composition of these two functions. So first I will find g of g inverse of x. Oops. So what this means is it tells me to take what they tell me the inverse function is and plug it into g of x everywhere I see an x. So this will be equal to the fifth root of x, all raised to the fifth power. And hopefully we know that the fifth root and the exponent of 5 cancels each other, and this will just leave us with x. And now I need to do it the other way and find g inverse of x, g inverse of g of x. So now I will be plugging in g of x everywhere I see an x in g. So this will be the fifth root of x to the fifth power, which again cancels and leaves me with x. So we just showed that these two functions are inverses of each other. Another example wants us to verify that these two functions are inverses of each other. So again, we will find f of inverse of x, of f of x. And so we will plug in the inverse function into the original f of x everywhere we see it in x. So this would be 4 times 1/4 x plus 7 minus 7. So I just plug that in to my function of f. And when I multiply the 4 in there, that'll cancel with that fraction. That's equal to 1, so that'll just leave me with x plus 7 minus 7, which is equal to x. So now I need to find the inverse of f of x. So I will be plugging in f of x into the inverse function. So this would be 1/4 times 4x minus 7 plus 7. So I just plugged that into my function for x here. So the negative 7 plus 7 will cancel. This will leave me with 1/4 times 4x, and those 1/4 times 4 is 1, so this is just equal to x. So we just showed that these two functions are inverses of each other. Next example says verify that the inverse of f of x, which is equal to 1 over x plus 2, is the inverse function of 1 over x minus 2. For what values of x is the composition of the inverse of f of x equal to x? And for what values is f of the inverse of f of x equal to x? So the reason why it's asking us this is because these two functions are rational functions, so they have restrictions. So I need to be aware of their domain. I cannot divide by 0. Have to always remember that. So the domain for f of x is going to be all real numbers except for the value of -2, because I can't plug -2 into here. And the domain of the inverse of x is going to be all real numbers except for x equals 0, because I can't plug 0 into there. So now let's find, we want to verify that these two functions are inverses of each other. So let's go ahead and find the composition. So first we'll find f of the inverse of f of x. So we will plug in the inverse function into f everywhere we see an x. So this will be 1 over, and now the x in the denominator here will be replaced with all of this. So this will be 1 over x minus 2 plus 2. I just put it in parentheses just to show you that I was plugging it in for x. But that minus 2 and plus 2 will still cancel, so this will leave us with 1 over x. Keep, change, flip, so this will just leave us with x. Step 2, we will find the inverse of f of x. So now we will be plugging in f of x into the inverse of x everywhere we see x. And so we get 1 over x plus 2 minus 2. So I plugged in my f of x in for this x right here for the inverse function. Okay, so that first fraction I can keep, change, flip, and that will just leave me with x plus 2. And then I still have my minus 2, and so this is just x. So they are inverses of each other, but only for values, all values of x except for 0 and -2. Okay, so what if they give us a function and they want us to actually find the inverse function? So here are the steps that we take in order to do that. So the first step is to interchange. If they give us a function y equals f of x, we interchange the variables x and y. So instead of y, I would put an x, and instead of x, I would put a y. I just switch them. And so this will give us the implicit version of the inverse function of f. So then we can actually solve, in step 2, we can solve the equation for y. And then when we're done solving it for y, we can replace y with the symbol of the inverse of f. And then, of course, we can always check in step 3 that when we find the composition of those two, that they are equal to x, just to check our work. For example, it wants us to find the inverse of f of x is equal to 3x minus 5, and then graph the original function and the inverse on the same coordinate axis. So again, the first thing, since they are saying this is f of x is equal to this, I can replace f of x with y to obtain this. Y equals 3x minus 5. And now I will replace, or I guess I can say interchange. I'll just say interchange the x and the y to obtain, so instead of y here, I'm going to put an x equals, and instead of this x, I'm going to put y. So I have x is equal to 3, y minus 5. Step 2 is to solve for y. So I have this equation, and now I am going to add 5 over to cancel it. This leaves me with x plus 5 is equal to 3y, and then I will divide by 3 to both sides to obtain that y is equal to x plus 5 over 3. And then I can exchange that y with the inverse notation of f. So our inverse function is x plus 5 over 3. So after this, you could check and plug them into each other to make sure that you get x, or we can graph them. They wanted us to graph them, so we will graph both on this axis here. We have the, let me make sure, okay. The pink one is the f of x is equal to 3x minus 5, and then the blue one is the graph of the inverse function. And you can see that those two graphs are symmetric about the line y equals x. So therefore this shows that they are in fact inverses of each other. Okay, so the next example, they're telling us that this function is 1-to-1, and they want us to find the inverse and then check the result. So step 1, I am going to replace that f of x with y. And then I am going to interchange my x and my y. And so that will give me x is equal to y plus 1 over y minus 2. And now I'm going to solve for y. And I have to multiply both sides by the LCD, which is y minus 2. So I multiply both sides by y minus 2 to cancel my fractions. That's why I'm doing that. I'll go ahead and distribute the x on the left, so I get yx minus 2x is equal to y plus 1. Because I'm trying to solve for y, I want to get all the terms with y on one side. So I am going to add 2x to get it to the right, and I'm going to subtract y to get it to the left. So that leaves me with yx minus y is equal to 2x plus 1. And now we need to factor out the y. And that will give me y times x minus 1 is equal to 2x plus 1. And then I can divide both sides by x minus 1. Cancel that. So the inverse function is equal to 2x plus 1 over x minus 1. Given that x cannot equal 1, and the original one, x could not equal 2. Sorry, could not equal 1. Okay, so here we are checking by finding the composition. So they're plugging in the original f of x into the inverse function. And if you remember, we just found the inverse function to be 2x plus 1 over x minus 1. And this is my f of x that I drew the arrow to here. So they're plugging in the f of x into this function here, everywhere you see the x. Then they multiply the top and the bottom by x minus 2 to cancel those denominators. So these would cancel after I multiply that by x minus 2, and they distribute that and then the x minus 2 would get multiplied by this 1 as well. And then again, these would cancel, and then that leaves me with what's on top, and then I multiply the minus 1 by the x minus 2, and that negative gets distributed. Combine like terms, and we're left with x. Now here, down here, we're plugging in the inverse function into f of x. And so, again, they're going to multiply the top and the bottom by that denominator of x minus 1. And it'll cancel on the first fraction, leaving us with the numerator, and then we distribute it to the 1, so we get x minus 1. On the bottom, it cancels with the first fraction, leaving us with 2x plus 1, and then we distribute it to the negative 2, and we get that. Combine like terms, and we get x. So for both of them, we do get x, and when we plug in the inverse here, remember x cannot equal 1, and when we plugged in f of x here, x cannot equal 2. So this one says to find the inverse of the function x squared plus 1 if x is greater than or equal to 0. So notice that this is the graph of a parabola shifted up 1 unit, and this is not a function for all real numbers. But if I cut this off for the x is greater than 0, then we're only talking about this part of the function. So that part is 1-to-1. So therefore, if we restrict the domain to x is greater than or equal to 0, then it will have an inverse, and we can find it. So again, we are restricting x to be greater than or equal to 0. And to find the inverse, we interchange the x and the y variable. And we obtain this equation, x is equal to y squared plus 1. So because we had to restrict the x here to be greater than or equal to 0, well, now we're going to have to restrict this y here to be greater than or equal to 0. This is the same equation, and we still want to, except for we're exchanging x and y, but we want to restrict that domain for y now. So now we are going to solve for y. So I will subtract 1 to both sides. And now to solve for y, we have to take the square root of both sides to use that square root property. So usually this would give us a plus or minus answer, but because we're restricting y to be greater than or equal to 0, we're only going to go with the positive answer. So this is the inverse function provided that y is greater than 0. And then we can check, and I will let you look at that on your own. Here is the graph of those two functions, and you can see that it is symmetric about the line, the y equals x. And for both of these, we have restricted, well, for f of x, we restricted x to be greater than or equal to 0. And for the inverse, we have restricted y to be greater than 0. But it's already kind of restricted because it's only the positive version of that square root. Okay, so that's actually the end of 6.2. I did want to go back to something that was in 5.3. I know I'm kind of going back pretty far, but I just wanted to review this. So in 5.3, we learned about the intermediate value theorem that said that if A is less than B and if f of A and if f of B, the outputs, are opposite signs, then it tells us there's at least one real zero between A and B. So I wanted to go over this example. So this says to find the positive real zeros, or the positive real zero of f of x equal to 2x to the 4th power plus x squared minus 1, correct to 2 decimal places. So I just wanted to review what this, or explain what this means. So usually they'll give you like an interval to start testing here. So in this example, they found, or they picked the two numbers to be between 0 and 1. So they want me to see if there's a real zero between 0 and 1. So when I plug in 0 here, I get negative 1, which is less than 0. And when I plug in 1, I get positive 2. So because I have different signs, we know that there is a 0 between 0 and 1. So I can actually keep going and divide this interval into 10 sub-equal intervals and use the table feature on a graphing calculator to evaluate f at the endpoints of the intervals. And then I can keep using the intermediate value theorem until I find really like where this 0 is exactly to 2 decimal places. So let me explain. So remember, we were using the interval between 0 and 1, and we did find that there was a 0 in between there. So if I separate this into 10 intervals, then I look here at this table, that means I'm looking at 0.1, 0.2, 0.3, up until 0.9. So you see, when I plug 0, I get that negative, and up until 0.7, they're all negative. And I'll erase this little part. And after 0.7, they start becoming positive. So now that tells me that this narrows it down to there being a 0 between 0.7 and 0.8. And you can see that the results there for 0.7 is negative, and for 0.8 it's positive, the output. So now I know that there is a 0 between 0.7 and 0.08. So then I can break that interval up even further into another 10 equal sub-intervals. So if you look down at this next table, they are breaking between 0.7 and 0.8. Now they're doing 0.71, 0.2, 3, 4, 5, 6, until 0.79. And you can see that at 0.7 it is negative, and after 0.71 it becomes positive, and all of these are positive. So therefore, now I know that my 0 is between 0.7 and 0.71. So then I can round to 2 decimal places, so the 0 it'd be 0.70. So I just wanted to go over that question with you. So please make sure you understand this. There will be a question on your test about finding the inverse, and there may be one about these intervals, but I'm not sure. I haven't made up my mind yet. But I'll let you know before. Thanks.